In this video, I want to talk about how we find bases for the row space, the column space, and the null space of a matrix. So we're given a matrix, in this case, this matrix A. It's a 3x4 matrix, and I want to find a basis for each of these three vector spaces that are associated with it. And as I mentioned in a previous video, in the process of doing this, we'll actually gain a lot of insight. We'll see that the rank of a matrix makes sense. That is, that the row space and the column space have the same dimension. And we'll also see why the rank-nullity theorem is true. All right, so let's get right into it. And I'll just pull up this list of what we do here. This is how we find a basis for the row space, the column space, and the null space. And let's go one at a time. So if we want to find a basis for the row space, we're going to convert the matrix to echelon form. We could go all the way to reduced row echelon form, right? That's an example of a matrix in echelon form, but we don't need to go all the way there. So that's our first step. And then we'll look at the non-zero rows of the matrix in echelon form. These will be a basis for the row space of the matrix. So let's convert this thing to echelon form. So this is one echelon form of this matrix. Again, there's more than one possibility. And what I just said was that if we look at the non-zero rows, these are a basis for the row space. Or in other words, row of A has this as a basis. There are lots of other bases of the row space, right? Any vector space has lots of bases, but the non-zero rows, once we've gone to echelon form, give us a basis. All right, great. Let's look at the column space. I guess I should mention this. If you're wondering how I got to echelon form, I did row operations, right? I'm not gonna revisit that each time we do an example. It would take too long. But I did a sequence of elementary row operations to take this matrix and turn it into echelon form, and I stopped at echelon form because I didn't feel like I needed to go any further, because that's not necessary. All right, finding a basis for column space of A. Well, the first step is the same. I need to convert the matrix to echelon form, and going to reduced row echelon form is not necessary, although that would be fine. And then I look at the pivot columns of the original matrix as a basis for the column space of A. Okay, so this is a bit more complicated. But what I'm saying here is that the pivot columns, here are my pivots. And so that means that the pivot columns are columns 1 and 3. And so I want to go back to my original matrix and take those columns. So the column space of A has this set as a basis. And importantly, I went back to the original matrix, right? I found the pivots and I went back to the original matrix. The whole point of converting was to echelon form was to figure out what the pivot columns were. So a little more complicated, but not so bad. Now let's find a basis for the null space of A. So finding a basis for the null space of A, well, I have to solve the system, right? The null space is the set of solutions to the system with this augmented matrix. And what I need to do is I need to solve that system. I need to write my solution set as a linear combination of vectors. So write my solution set in vector form. And then the vectors that are having linear combinations taken of them, those will give us a basis for the null space of A. So definitely a bit more complicated, but also something that we've done previously. So let's see how this looks. So for null of A, I want to solve the system corresponding to the augmented matrix where the left-hand side is A. So let's just copy that. and the right-hand side is zeros. That's what the corresponding homogeneous system refers to. And when we solve this, we've talked about this before, we convert it to reduced row echelon form, and what we'll end up getting, so this is a sequence of row operations. Again, I'm not going to do this every time. We get 1, 7, 0, 2, 0, 0, 1, minus 2, 0, 0, 0, 0. We've talked about this, that the right-hand side is always just zeros. And with homogeneous systems, it doesn't really matter. I mean, it matters in the sense that it affects the solutions, but the process of row operations doesn't change the right-hand side. And so what we actually have here is the reduced row echelon form of A. Right? We could have just ignored the zeros in doing the whole computation. Okay, so I solved this, or I started to solve it. So what are my solutions? So my free variables are x4 and x2. So I'll name these parameters. And then when I solve this out, this equation tells me that x3 is 2 s1. This equation tells me that x1 is negative 2 s1 minus 7 s2. And if you're kind of confused on those steps, go back to solving linear systems. Just remind yourself of how to do this, right? I rewrote it as an equation and worked out the answer, but I just did it in my head. Now we need to write this in vector form. And as a vector form, this ends up being we have two pieces. We have the S1 piece and the S2 piece. And so in the S1 piece, we have a negative 2, a 0, 2, and a 1. And in the S2 piece, we have a negative 7, a 1, a 0, and a 0. And these two vectors form a basis. So this is a basis for the null space. All right, so I've gone through all three possibilities, all three examples of vector spaces: row space, column space, and null space. And they all involve converting to echelon form, or in the case of the null space, reduced row echelon form, and using those answers to figure out a basis for the space. So I found all three bases, but I want to give a few quick warnings here. So with the row space, remember, I converted to echelon form. Let's get rid of these extra things that I wrote. I converted to echelon form, and then just fix this matrix. All right, so for the row space, I converted to echelon form, and I used the non-zero rows in echelon form. But it's important that I use the non-zero rows in echelon form. I need to keep things straight. If I got confused with column space and said, oh, these are the non-zero rows, and went back to here, this isn't necessarily a basis. That is, these two rows, in this example, these two rows are multiples of each other. And so they definitely don't form a basis. They're not linearly independent. So I have to use the rows for row space. I have to use the non-zero rows from the echelon form matrix. For the column space, it's really important that I use the pivot columns not in the echelon form matrix, but from the original matrix. It's actually pretty easy to see here. If I tried to use the pivot columns from the echelon form matrix, I would never get anything other than a 0 in the third entry, right? Because these have 0 as the third entry. And so those can't really be a basis for the column space, because we can see that, yeah, there are vectors in the column space that have non-zero entries in the third entry. So those are two warnings. For row space and column space, be really careful which matrix you're pulling the vectors out of. It's not the same, and it matters. For null space, it's just a quick warning that you may already realize because you've worked with this enough. Even as someone who teaches this class and who has done this a lot, I'm really careful. It's pretty hard to read this answer from this matrix. I mean, you can do it with enough practice, but I tend to think that unless you're really feeling comfortable, it's quicker just to write out the solutions, write them as a vector equation, and write out the answer than it is to try to do it in your head. If you try to do it in your head, you're just going to get it wrong a lot of the time. Maybe you'll become comfortable enough that you can do it, but I kind of warn against that. The final thing I wanted to point out in this kind of warning section, it's not so much a warning, but if we want to do row space and null space of A, we could have used the reduced row echelon form of A. And so what would have happened? Well, with the column space, we would have gotten the same answer because the pivots don't change, right? And so we would have identified that the pivot columns were 1 and 3 and gone back to our original matrix, and we would have gotten the same basis. For the row space, if we went all the way to reduced row echelon form, we would have said, okay, our basis is 1702 and 001 minus 2. And so we would have gotten a different basis. It's still a basis. It would just be a different basis. So if we use different echelon forms, we'll always get the same column space basis, but we'll get different row space bases, and that's fine. But they will be different. And I'm going to finish this video by talking about why this process works, right? I just showed you how to make it work, but I want to point something out before I do this. We can see two things here. So back to the Rank-Nullity Theorem. This process shows us why, 1, the dimension of the column space and the dimension of the row space, the thing that we're calling the rank of a matrix, are equal. And it also shows us why the rank plus the nullity is the number of columns. And what do I mean by that? Well, let's go back to finding the row space and the column space. I'm not just saying that this example gives us the same answer. When we find the row space, we're looking for non-zero rows in echelon form. How many non-zero rows are there? Well, there's one non-zero row for each pivot. Each non-zero row starts with a pivot. And when we're trying to find a basis for the column space, we're looking at the pivot columns. Well, that's also just the number of pivots. So what this process really showed us, if we're trying to think kind of more generally, is that these are both the number of pivots. The dimension of the column space and the dimension of the row space end up being the number of pivots. And so that's why these two dimensions are the same, right? Or one of the reasons, an explanation why they're the same. We can apply similar logic to this. Well, the rank of A, we've just said, is the number of pivots. Well, what's the nullity of A? Well, when we solve this equation to figure out the basis for the null space, we see that we get a basis vector for each parameter. And we already know that we get a parameter for each free variable. So the nullity is the number of free variables. But we already know when we're solving homogeneous systems that every column corresponds to either a pivot, is either a pivot column, or it corresponds to a free variable, right? A free variable is a column without a pivot. This is kind of it's just by definition what it is. And so every column is either a pivot column or it corresponds to a free variable. And so when we add up the number of pivots and the number of free variables, we get the number of columns. So this process has just kind of proved for us these really nice facts. I want to finish the video with one kind of even next level thing, which doesn't necessarily shed light into how to do this. And so if you're just trying to solve problems, you don't even need to watch this part of the video. But I want to talk about why this process works. And so in particular, I want to say, look, why, pull this up. Yeah, why do the non-zero rows of the matrix in echelon form, why are they actually a basis for the row space? Why do the pivot columns of the original matrix give us a basis for the column space? And why does this work for the null space as well? And so I won't spend too much time on it, but I want to look through these examples and hopefully make it clear why this is true. Okay, so let's start with the row space. Why did these two vectors give us a basis for the row space? Well, how did we get here? This whole arrow here was me skipping over a bunch of work I didn't want to do in a video. It was a series of row operations. And in row operations, what we're doing is we're switching rows around, right? We can flip them. We're multiplying rows by constants, and we're adding multiples of rows to another. But doing that doesn't change the row space of a matrix. So this is, I don't want to flip back too much. But so why this works. For the row space, row operations don't change the row space. You just can think of each individual elementary row operation and convince yourself that the new matrix that you get has the same row space, because all we're doing is switching things around or creating new linear combinations, and we're not losing anything. So this new matrix over here, the echelon form, has the same row space as this matrix. But once it's in echelon form, it's pretty clear of two things. Because of the staircase shape, it's pretty clear that these vectors are linearly independent. Right? There's no way that I could get this first row as a linear combination of later rows because they have zeros under the pivot. There's no way I could do that. So it's clear they're linearly independent, and we don't need any of the zero rows, right? Those would never be part of a basis. So once we get here, it's pretty clear that this actually is a basis. So that's why this works for the row space. Let's think about the column space, because the same logic is not going to work. This one example already shows us the column space of this matrix is not the same as the column space of this matrix. Every column of this matrix and everything in its column space have zeros for the third entry. That's not true here. So why does this process work for column space? And this is, I think, super interesting, and we'll see an example of the fact that I'm about to show, which is that for column of A, yeah, we're changing the column space, but row operations don't change dependencies between columns. So what do I mean by that? I mean that if we look at our echelon form, we can see that 2 times column 1, let's put it like 2 times column 1 minus 2 times column 3 equals column 4. Let's go to echelon form, because it's much clearer in echelon form. 2 times column 1 minus 2 times column 3 equals column 4. Just convince yourself that that's true as vectors. And then we look at our original matrix A. 2 times column 1 minus 2 times column 3 equals 2 times column 4. That dependency is still true. And this will always be the case. Doing a row operation, you're doing the same thing to each column. In the sense that in column 1, you're adding, if I add 2 times row 1 to row 2, I'm adding 2 times the first entry to the second entry, and I'm doing that to all the other columns. And what this means is that any dependency that we have won't change. And so once we get this to echelon form, we can see, hey, wait a second, dependencies haven't changed. And in this new matrix, it's pretty clear that these two vectors form a basis for the column space. For the same logic as talking about the row space, right? And then we have to go back and say, okay, well, if these form a basis for this new column space, then in the original matrix, since dependencies don't change, these two corresponding vectors will form a basis for the column space. So I think harder to understand, but the idea is this. Row operations don't change dependencies between columns. And I think one of the easier ones to understand is why this process works for the null space, which is that we wrote our solutions as a linear combination, so definitely spanning, of linearly independent vectors. So let's look at this solution here. We're saying that all solutions can be written as a linear combination of these two vectors. So certainly these two vectors span the null space. Why are they linearly independent? Well, you just have to look at the free variables. When we write this out, we're always going to have, if our free in a free variable, so for instance, x4 is the free variable corresponding to S1, we have a 1 in the S1 matrix, and we're going to have zeros everywhere else. And similarly, x2 is the free variable that corresponds to the parameter S2, and so we'll have a 1 there, but all of the other second entries are going to be zeros. And that forces these vectors to be linearly independent of each other. So that's why this works. And again, seeing why this works is not really necessarily even useful in solving these problems, but I do think that it's valuable to have seen why things work at least once, because at least for me, that makes them more believable. So again, this is our process. We have a very straightforward algorithmic process for finding a basis for row space, column space, and null space. Just really be careful with those warnings. You want to make sure you know where you're pulling the vectors from. Sometimes they come from the original matrix, sometimes they come from the echelon form matrix, and sometimes, in the case of the null space, you really just kind of have to write it out. They don't materialize in some nice way.